Warm round of applause for your presenter today. It's kind of weird. So, have we started?
Yes.
My name is Xiyang Chen. I'm a machine learning engineer at Rango. Repeating this just for the video. And today, I'm going to be talking about doing a code review, primarily looking at the code of the transformer. And Felipe and Ehsan will be the expert/facilitators for today. So here's our outline. We're gonna tell a little bit why we are interested in transformer and the PyTorch versus Tensorflow debate, as some of you are probably familiar with. And then we're gonna go over an overview of the architecture. And then we're going to break them apart and look at the code block for each individual block. And finally, put them together and look at how training and experiments is done. And then the floor is open for discussion. Before I move forward, how many of you have worked with transformer before? Not many. Oh, you have. Okay, how many of you are familiar with attention? About half of the crowd. Okay, cool. So here's a little bit of motivation. I forgot. Oh yeah, by the way, GDLs has already done a session on transformer, but that one is mainly focused on the math and the paper. That one was done by Joseph Parallel. It's on YouTube, and feel free to check it out. So why are we doing code review? This is a brand new session, experimental format. I think the first and foremost code review allows us to just look beyond the math, because there's not a lot of things not said by math and text in the paper, and a lot of things you probably have experienced. Like you look at the paper and it says one sentence. We apply this technique. Behind it, there's like maybe 100 different things, which then you have to refer back to like a whole bunch of other papers. So hopefully, code is a ultimate ground truth that could hopefully potentially capture all that. And also there's some kind of a lot of practical constraints. There's a lot of decisions that you will not realize until you actually look at the code. For example, you're maybe constricted by memory. A lot of these architectural decisions might have to do with that. And wall clock time. Usually when this paper publishes paper, there's a deadline to catch. So there's like practical trade-offs. And maybe it has to do with source code availability, like how easy and hard, and you look at that angle or dimension, and then maybe, hopefully you realize something new. And as I mentioned, hopefully you're seeing things from sort of like 2D to 3D by having an extra dimension that you can reference. And also, this is what I call the poke, observe, and believe mode, which is basically being familiar with code can allow you to do a lot of small experiments to test your assumptions. Because I ran into so many times when I was preparing this, like I thought I understood, then I look at the code, I'm like, oh, actually I was wrong. So, and it also finally allows us to be lazy. So part of the reason we started TDLS, because at least Amir and I, we are lazy. We want other people to explain the paper to us. So tonight, it's me explaining to you. Hopefully you get something, but hopefully next time it's me sitting there and someone explaining things to me. So that's the rationale. Highly experimental. So this is by no means the correct format. Also, by the way, I'm doing this with slides, but nothing prevents you from actually running a Jupyter notebook. Because we had, as of yesterday, we had a constraint where we have to do PDF slides, but I think that constraint was solved. But I was already like 30 slides into the preparation. So specifically, why do we care about transformers? How many of you have heard of transformers? About most, okay, 70% of you. So some people describe it as Google doing it. It's done by people at Google, researchers at Google. Some people describe it as Google doing attention to the stream. So to the point where you can, in the sequence task, like the RNN is completely got rid of. And practically speaking, it achieves a lot of state of the art. A lot of architectures employing transformer achieve state of the art. The latest one, BERT, I'm sure a lot of you have heard of. They use it to do a lot of NLP tasks like question answering, and then they just a lot of times be the second place by a wide margin. And transformer is the foundation of that. And this new thing that came out like 2, 3, 5 days ago, we're counting these things by days, like transform by this company called Hugging Face. They presented at NeurIPS, but I don't think that paper was ready. And then I think they did some work and they published this. It's very similar to the way how it works with BERT, but in this case, they're using it for conversational dialogue generation. And there's this thing, I'm pretty sure this thing came out like 3 days ago. It's called Transformer XL. We might have a paper presentation session coming soon. We're still confirming that. Also done by Google. There's some other very interesting work, to name but a few. The latest one, AlphaStar, uses transformer as part of its network. It's like transformer plus sequence, LSTM or something. And if you look at Google Scholar, right now it's being cited by over 1,000 times. And ultimately, a transformer is a lot faster and more scalable. We're comparing transformer with other sequence-to-sequence model that employs RNN here. And everything is pretty much parallelized across time span. That's what we'll see. So then there comes the PyTorch versus TensorFlow debate. I checked officially. The official version is down in the tensor-to-tensor repository with like TF estimator and TPU support and a static graph, all that. Which we'll probably touch upon that a little bit. But however, a lot of people say a lot of good things about PyTorch. So we have a dilemma, which, what's that? Okay, but I believe as engineers and scientists, we should look at this thing in a very objective, rational, scientific and methodical manner. Objective, yeah. We need to analyze. Okay, I'll give you an example. Like this is a comment I think is great. Okay, I just realized recently how easy it is to start, like, in the coding, like, developer community, there's like programming language wars that's going on. I just realized how easy it is to instigate a programming language war. But this is jokes aside, I do have a slide that actually lists all the pros and cons of the architecture choices. So I consulted people on the Slack channel. So I guess this is the thing that we end up coming up with. And I think Felipe has some other comments. First of all, PyTorch is really good for popular among researchers, mostly due to its flexibility, as opposed to in traditional TensorFlow where you have to construct static graph. So there's kind of like a layer of indirection and abstraction. And if you look at how it interfaces with CUDA, I don't know why, but it just feels a lot faster. However, TensorFlow is usually perceived as more production-friendly and production-ready. However, PyTorch, I think, is rapidly catching up. Some people, I forgot, send me a video about that. And did you have anything to add?
Yeah, like the PyTorch has something called PyTorch scripts. That is a decorator that you can put to many objects in Python that will help you move many of the code to production, because you can create basically like libraries, like things that you can call from C programs, and those are easy to serialize.
Okay.
Sorry, is that a superset of O and X?
Sorry?
Is that a superset of O and X?
I don't know.
So specifically for TensorFlow, they have kind of out-of-the-box in a way solution, I think, which I know is very attractive, like say data scientists. TF serving gives you an interface, both in, they're using like their own Google protobuf or something, but you can also get a RESTful API. Whereas the area in that part with PyTorch, maybe they're working on something, but I'm not sure. And among other things, the other thing is like platform. I'm struggling to find the term. Is a form factor or platform? It's basically, sorry, not the point. This point is, if you look at if you want to search something in the cloud, a lot of these platforms say we support both PyTorch and TensorFlow. But practically speaking, if you look at the amount of examples, it's heavily favored towards TensorFlow at this point. But they do. I know at least like AWS has like PyTorch examples, just like there are less.
That's probably just because TF has slightly more documentation, and it's easier to use in like mobile applications and things like that. It has nothing to do with the cloud, right?
So for this specific point, what I mean is like if you say look at AWS, like AWS, like say SageMaker. If you look at the examples, number of the examples, say written in TensorFlow versus in PyTorch, I got a feeling like there's a lot more examples. That's what I mean. But I do have that point. TF spans a lot more platforms than PyTorch networks. That's the other advantage. So far, this I probably lost count. It supports TPU, GPU, CPU, and it has TF Lite. And there has been recently some really interesting coming out in TensorFlow JS, where they pour like PostNet. It's only like 10 megabytes of download. Google really spent a lot of effort, like quantize, optimize so that it's downloadable. And it can also run in Node.js. So TFJS is actually, you can both run on the server and on the client. If you do it on the server, they introduce CUDA. If you run on the client, they introduce some WebGL limited acceleration, but there's still acceleration. And finally, there's a new thing called Edge TPU, which I don't know much about, but it's in beta, and you can kind of sign up. I don't know if it's available in Canada, but there's a sign up form.
It is.
So it seems like there's CPU for edge devices. Is that?
Yeah. But it's an older architecture.
So I don't know if TF will support that, but I'd be really surprised if Google doesn't support that. TensorFlow doesn't support that. Well, the other thing, big argument is like performance. Definitely, static graph mode is a lot faster than like interleaving Python code with interleaving with Python code. However, as mentioned, it's cumbersome to code with because there's a layer of. In order to tap into it, you kind of have to do a lot of indirect things. Correct me if I'm wrong. So, however, this Google responded with TensorFlow eager execution, which is, I think, I look at the API, it looks very similar to the way PyTorch and MXNet works. Do you have any comment?
I think it's still variables.
It's still variables, okay.
Yeah.
That's why I said it's very easy to start a language work. So.
There's also Swift for TensorFlow where you write in.
Oh yeah, thank you.
So you write like eager execution, you write imperative code, and then the compiler extracts the graph for you, so you never see it.
Okay. Yeah, and you mentioned the point on Slack. Like also supports other languages, such as Swift. I know someone who's working actively on Tensor. It's not perfect. It's like Swift versus TensorFlow. They're working on another version. So there's all these language choices. I think they still would like to construct static graph in eager mode, and this is, I think, what they came out with. It's called autograph. So it's I'm not exactly sure how it works, but basically you code in Python, but behind the scene there's probably some kind of parser or interpreter that translate that into like a for loop or if statement into static graph. I think that's how it works, but I could be wrong.
I think it just dynamically constructs the graph for you as you go on. I think that's the difference.
And then they announced that it will be the default, eager mode will become the default mode in TensorFlow 2.0. However, I need to put a word of caution here because I tried this personally. I think because it's too new. And there's still a lot of incompatibility. Like basically the land is buried. And you are the new pioneer. Like if you want to translate anything into TF eager mode, then you probably gain some fame right now. But because I think they expect that Google is spending a lot of effort to do a lot of things in eager mode now. But if you try to port those code directly into eager mode, a lot of times they don't work for various reasons. Okay, so with all that said, unfortunately we've got to pick one. But I looked online. The one that is clearly explainable for this particular case for transformer is still in PyTorch. I think I found 3 or 4 ones. So for tonight, we're going to be doing PyTorch. And I'm going to do a little preliminary just for those who are not familiar with PyTorch. We're going to use this annotated transformer. I think this is like one of the more famous posts about the transformer. And they do a relatively faithful implementation from the original paper. I was happy with this until this morning. I opened up my laptop and like, damn, and because someone just came up with something that's simpler, more concise, and I think they just published like a few days ago. However, I was like 30 slides into the preparation, so I don't want to change anymore. But what I mean is, by no means, there's got to be a version that's good for you. But for now, please just bear with this implementation. There's something I like about it. There's something I don't like. I think sometimes the annotated transformer overly used abstraction, which kind of obscures the understanding. This one is done by Harvard NLP, annotated transformer. Okay, any questions before I move on? Yes?
What is the source that you mentioned?
I have a reference page in the end that lists everything. But I'm borrowing ideas from all these like different transformations. Yeah, check out the reference slide. Yeah. I'm going to show you. So here's an overview of the transformer. It is essentially an encoder and decoder mode. How many of you are familiar with encoder and decoder mode? Sequence to sequence. About half. Oh, more than half. Okay, very briefly, because a lot of you probably are more expert than I am here. We're talking in the context of dealing with sequences, such as text. For example, translation task, where you have your input is a sequence, your output is also a sequence. Think of like English to French. The way essentially encoder and decoder work abstractly on a high level, you use an encoder to take in your sequence. It could be an RNN, but in our case, this is a transformer. And then there's also I forgot there's a laser here. Okay, cool. There's a bottlenecking here, where you kind of squeeze things down into a dimension. It could be 122, 128 to 256, 512. A certain dimension vector where it's being fed as the starting point of the decoder. So there's a bottleneck in there, which kind of like, in a way, what's the right word, compress or distill information. And then toward the end, the decoder takes in that initial state and then produce the sequence that you want to train on. So this is supervised learning. So this is encoder decoder at a very high level, and this, which I pretty much inserted this into every single slide because there's a lot of information here. This comes from the paper, Attention is All You Need, the transformer. So we will be going over this over and over again. Just to, oh, sorry, I think I made a mistake. I forgot if the input size is 512. Actually, oh yeah, I'm right. So to simplify the entire structure, the input size and output size of a lot of these blocks is set to the number 512. So you're going to see like 512 a lot. Like, you will probably see that there's an X here, which means this part is being repeated n times. I think in the paper it's six times. And in here, it's repeated 6 times. And then there's a little thing that goes here, which kind of corresponds to the bottleneck I was talking about. But in here, it is a attention mechanism. So the left part is the encoder, the right part is the decoder, and we will go through in the details. I'm going to just try to get enough so that we can look at the code, but for more details, please refer to the other video or there's some other materials. But if you don't understand something, please stop me. So this is another way of looking at this. So in practically speaking, when you train this, you can parallelize this. And this is how it is being run, I think, inside a GPU. So you have essentially 5 stages, but the encoder and the decoder can be trained in parallel on stage 1, and then move on in parallel to stage 2, and move on in parallel to stage 3, and then you have 2 additional stages, and stage 4 and 5. So target data, the input here is, there are 2 parts. So there's the input and there's output. The name is probably slightly confusing. What I mean by input here is, okay, let's just stick to the example, English to French. This is the English, and here's the French. However, what's more confusing is when you output, when you produce, there's also French produced here. This is what you're produced. But this is a reference. The way it works is basically in order to translate your language, you definitely need to know the English. However, you're also allowed to know partially the French sentence. For example, if I am translating the 3rd word, like say the English is, what's the next example? I am a student. What's the French word for that, of a sentence for that? Okay, whatever he said. The third word. Suppose you're working on the 3rd word right now. Like, what's the 3rd word I'm going to output? I can be aware of the entire English sentence. I can also be aware of the first 2 French words that is already done or produced. So that is my context. However, I'm not allowed to know what the current word is. Otherwise, it would be cheating, because I'm essentially looking at the answer. So from the 3rd word onward, everything is masked. So that is why you are allowed to look at the input, and here output is misleading because it's also, they kind of serve as the input, but that comes from the encoder-decoder literature, so they call this input and output. Okay, any questions so far? This is part, I have to clarify, they're using KL divergence in this annotated transformer in particular, but I've also seen other implementation that uses cross entropy. As to which one you choose, I'm not entirely clear. If anyone has some insight, let me know. So let's move on. So here's another more clear diagram I stole from another blog. This is basically, from now on, we're going to start drilling into the details. There are 2, I guess, like noteworthy part, which is the first part is called multi-headed attention, which is in here, and in here. And also, we're going to be talking about positional encoding and how they do masking, as well as the loss function construction under both single GPU and how you do that in multiple GPU. So here are some preliminaries for those not familiar with PyTorch. Oops. Did I do something horrible? Did you lose the Hangout?
No, I haven't.
Oh, you haven't. Okay. What's going on here? Okay. Okay, I probably need to. That's kind of weird. This is new.
Unplug it.
Unplug. Maybe I'm not going to lose the Hangout. Okay. Bear with me for a second. I need to share the screen again for the remote folks. Oh, by the way, we have some people who are joining remote. If you can hear me, welcome. What's that?
You mean the whole world?
The phone world?
The whole world.
The whole world is watching. There's a live stream right now.
No question. I think the last number of views is like 2 million and something.
Okay, cool. Thanks for telling me. Okay, cool, awesome. So, how many of you have worked with PyTorch before? About half. In a nutshell, it's impossible to go over all of it. There's a lot of good materials there. But just to get started, the way you construct a module, by module I mean any parts. It could be a layer, it could be 2 layers, or it could be an entire model. I think they all call it module. You basically superclass a subclass from the dot module, and then the next thing you need to do is you need to supply your class with 2 functions. One is called init, and the other is forward. We'll be seeing that a lot. So init is when you actually I think in programming language terms it's called instantiation. I don't know the term in PyTorch. When you instantiate, you basically start building a few other modules that basically the building block is ready. And then when you supply the forward, in the forward, you actually, usually there's an input, something goes in. And then you start calling all those building blocks. And you kind of string them together, kind of piping them together. That is when the actual computation happens. We'll be seeing that again shortly. And then in this particular example, I realized the Harvard NLP folks love using abstraction. Like I think in programming language terms, it's called higher order functions. It's basically a function that returns a function that returns another function, and then returns a class, which is basically like inherits from a module. And in that class, the thing that returned, you can still use it as a function. But the last part is actually comes from the PyTorch. So they have some very clever implementation trick where I think they do the like internally do the on the dash core. Felipe told me that. So, oh yeah, here. So eventually the end result is if you want to you have an input, and you can just call your object like use an object like a function, and call that function, feeding the x, and you get some other values, y. And this is interesting, and any object which is of type variable or parameter, I forgot which one it is. Parameter, okay. Anything like, let's say if your x is a parameter, and say in your instantiation, here you attach that to your class, which means this, oh no, sorry, this is Python. A self dot something equals something. Basically, that's what I mean by attachment. It is automatically added to the gradient computation. So we'll see. And then it's like when you do, actually when later you do backward, which means like you start doing gradient computation, that part will automatically be computed unless you suppress it. And there's a way to suppress that. Okay. It will become clear in a second. So here is, now this is first piece of code. This is a very generic higher order abstraction of how you do encoder and decoder. So in the, unfortunately I omit the init part, but you'll see another example. But in the forward, usually it comes, a few parts gets passed in. And essentially what is happening here is you call the encoder, which processes the source, which corresponds to this part, and then along with a source mask, which I think we'll talk about in a little bit. And then you essentially, with a source mask, and you take that result and feed that into the outer layer, which is a decoder. And along with what you get, which is essentially this line here. And essentially with that line, you also input the target, which we just talked about, which is the partial French, and also the target mask. Yes?
What's the mask for?
Masking is for, remember if you want to translate, say, the French, like this entire sentence, right? If you want to translate the third word, you are only allowed to know the first 2 words. You're not allowed to do the subsequent one. So that part needs to be masked.
I think we're getting clear in the video, that's why we're turning off.
Sorry?
It is fine now.
It's fine, okay. Okay, cool.
There's also a shift in the output. What is that for?
The shifting, I think it is for you, is it in here?
Like in the diagram that you have? When
Oh,
it
it's
says
shifted
output,
right in here.
It says shift to the right.
Okay, I think I knew this morning, but let me try to remember why did it do the shift. So you want to look at, so this is your reference, right? This is what you try to produce, and this is your reference. So in your reference, I think for them it's easier if they shift it one to the right. So for example, if your target is the third word, and if your output is exactly aligned, then then this part is also what you want to mask is also the third word. But however, if you shift your input one way to the right, then this becomes the second one. So you only, I think computationally it's probably easier. So this is the third, you try to predict, and originally this is the third, and you shift one right, and this becomes the second, and then before that, this becomes the first. So you only know like first and second. I think that's the reason why they should shift it right. I think, but that, I'm not exactly sure. So now we get into the encoder part, which is the input. So basically you feed in the English, and then it goes through this encoder portion. So if you drill down, this is essentially going to go through the sublayers, which we're going to go into in a moment. And I think this, and we also have something called a feed-forward network. So this is the part why I do not like the Harvard NLP, because this is not exactly clear. But I think what I want you to get out is they're first applying a self-attention, which corresponds to the arrow in here. And then they call the abstraction, which is called a sublayer, and which gets fed into the subsequent parts. And then this entire encode layer corresponds to one copy of this, and then you have n times, and then you repeat that with 6 times. Yes.
When you say n times, you mean front to back, so like that would put it the first 0 goes
Yes.
into 1. Okay.
So yeah, this is the input, and this is output. So the next input for the next layer is output from the previous layer.
What is the sublayer here?
Sublayer, I think it is. I think we'll be seeing that actually. I think it's probably in the next slide. Let me see. Yep, here. This is sublayer. I'll get it in a moment. So before I answer the question, so this is a single layer, and the way you construct n layers is essentially in the for loop. In the computation, you have a for loop, and first you store all the layers and use the clone method to clone them n times, and then you just iterate over. Like this x keeps changing all the time. Like every time x becomes a new value and gets subsequently fed into the next layer, and you get a new value of x. And then to answer your question, what is sublayer? This is exactly sublayer. So again, this part is the same, just to keep as a reference. The sublayer consists of a layer norm, and I think we have it's basically layer norm regularization, which I also have code for. And then at the end, there's also a dropout, which I don't think is shown here. So this is basically some regularization techniques. We're not going to be focusing too much on this because these are essentially, even if you get rid of them, you can still probably get some results. It's just like if you add these things, they will become easier.
It seems to be doing the add a norm.
Where?
So you see the yellow sort of rectangles?
Mm-hmm.
It seems to be doing those. It's a normalization and an addition.
Okay, let me.
And it does talk about the residual.
That's why I have this.
It does.
This is more spelled out. So you have, it's basically this part.
Yes, exactly.
Drop out and then layer norm, and drop out and then layer norm.
Yeah.
This is the part. And then so the way you connect it, then you have multi-head attention, sublayer, position-wise feed-forward, and sublayer again. So very similarly, now we move on to our decoder part, which is the right side of the particle. This is pretty much the same, except it's this is a single decoder layer. Except the only difference is it's taking in. It has more layers. Number one, it has another like substructure And in that substructure, it takes in the information from the encoder. That's the only difference. Otherwise, it looks pretty much the same with the encoder architecture. Again, decoder is repeated like n times. I think the way, here is, you can see here, like in the previous one, in the encoder, we only have self-attention. But in here, we also have source attention, which is basically gets passed down. So first you got a result from the self-attention, and then you pass that into the source attention. So there's this basically additional extra layer inside layer thing. So just a refresher of what attention is exactly. So there's this query key value paradigm that helps explain like self-attention, attention in general really well. Just to give you a formula for those who are more mathematically inclined. Essentially, the way it works is the best way I look at this is I look at like it backward. So what is the thing that you try to achieve? You have a bunch of things. They could be features. They could be, essentially, you have a bunch of numbers. You want to know which of this number are more important. In other words, for each of number, you want to assign them a value. That's essentially what attention is. Practically speaking, that value is between 0 to 1, which highlights how important my particular value is. So the way you achieve that, so if you look at many values, and each having a attention score, then you have an attention map. So which translate here, this is a very simple scaled out attention. So here's a value, and this part, like what the software outputs is essentially your attention map. So, and then the question is, how do you get that attention map? The way you get an attention map is essentially this formula. Then you have something called a query, and you have something called a key. So your query say in the case of encoder and decoder, in here, like, let me repeat, like in here, this part, this part from your decoder is your query, which means like if say I'm translating from the third word, I'm working on the third word in my French translation. That third position is my query. And so what are the keys? The keys are everything from the English. Like all the single word, like say I am a student, which is how many words? 4 words. Those are your keys. And essentially, if you do a dot product between the query and the key, and you do some additional thing, scale, and this mask is usually optional. We can ignore that for now. And if you have many positions, many key positions. So for example, you have 4 positions, 4 things from your English, then you can have a soft max. You can soft max them and so that their sum is equal to 1. So then you've got an importance on each position from the source. Does that make sense?
Can you have a window for your sort of attention? So let's say you're at the third word, right? So can you have like an attention window that you could say, okay, the previous 2 is right now at my attention window, and then I'm just focusing on those 2.
I think you can potentially window it into, if your assumption is that if you have very, very long things, yeah, you're saying like, I'm pretty sure that only this part is correct, right? Like you can have, but then there's the other question, like then it seems like you're doing something very similar to convolution. So I'm not sure exactly but I don't think anything prevents you from windowing it. So if your task is a particular task, like doesn't care about like things like in a very distance. So
but just a quick note. So you'd want to do that usually with RMNs because first of all, it's a for loop, and you can't really move to the next before you finish this, and because of this long sequence of sort of layers and time steps, you explode your memory. But here you're doing things in parallel. So you're less incentivized to do that because everything is going through your batch. But a very good question.
Okay.
Sorry, question. So what is this key to the power T? What's that key?
Transpose.
Oh,
T, transfer T.
Yeah.
So, in the original paper, the way they describe it is it's easier to start off by looking at a single thing. So if your key, query, and value, if you just look at one position, whether being your key or query value, then every time you get a vector. Like in our case, it's 512 vector. So the way you get attention is essentially you dot product them. Then you get a single value. That's when you dot product Q and K. You got a single value. And for that single value, that is usually for a particular position. But if you stack them up, then instead of a vector, you get a matrix. So the way the dimension along which you stack is basically your sequence. So for example, if your maximum sequence length is 10, then you stack up 10 things. And it turns out that if you do the matrix multiplication instead of the dot product, you end up getting, instead of getting one single thing, you get a list of things. And then that is essentially enables you to compute all these attention maps in parallel. Does that make sense? Yes.
Is the position encoding proposed in the original paper?
Sorry?
The position encoding, I remember that.
Is it proposed in the original paper?
Yes.
Position encoding, yes, but they did not invent that, but they modified the formula. But I don't think it's relevant to this.
I'm not sure because I was under the impression that position is irrelevant in the original paper. They just use the word encoding, but not the position encoding. That's the earliest transformer.
I thought they did, but regardless, let's move on.
They use position encoding, if that's a question.
Can you give me an example, please, for that matrix at the end, like 10 to 10? What does it mean in your English-French example?
So if I'm looking at the first layer, like which is actually relatively more legible, like say if my English I am a student, then you translate that into a vector of 512. Usually before you do that, it goes through another embedding layer. But just for the sake of simplicity, suppose your vocabulary size is 512. I think we can assume that. So you translate from the word I into 512 numbers. That's essentially one row in here. Oh, sorry. This is your query. This is your key. So I'm thinking English to French. So in English, this one column is I, and the second column is I am, third column A, and fourth column student. And your query is essentially the thing you care about in French. So this is the position from the French position. And here, each row represents a word, roughly speaking.
So 10 represents the words, like all English words or all French words.
10 represents the max number of words you can have in that sequence.
So at the end, we have a mapping.
Yeah, so eventually you have 10 by 10 attention map. I wish I could have like more, because you see a lot of this attention map illustration, but I don't have one. But I wish maybe I could pull one up like later. But essentially, here the rows are like I am a student, and the columns will be how important those words are to your calculation. So maybe sometimes it's a soft attention is attending to multiple things, which has to do with my grammar and the order of a particular language. And in the paper, they also use a scaling factor just to keep things in check, because they said empirically, if you don't scale this down, if you just keep multiplying them, essentially, I think the softmax has some kind of weird shape where the value gets too big and then it becomes saturated, and then that hurts computations. You have to like proactively scale it down by this factor. So that's essentially it. Yes.
So in the query, I see 10 there. So what usually are the dimensions for query? Like, can we define it ourselves, or?
It's, you can define dynamically, I think, for your task, for this case.
Hyperparameter or?
It actually, yes, it's actually, yeah. Okay, let's move on. And just, yes.
Could you go back to the previous slide? Are the dimensions that you're using exactly the same as the paper?
Sorry, which one?
You had tensors, and you had 8.
This is stolen from another simplified example.
Okay.
This is not. 8 in the paper is 512. Yeah, sorry, this is like just basically like toy example. So to complicate things, actually, this paper has 3 types of attention. The one I talked about was essentially encoder-decoder attention, which is like, this is the upper right corner. The right-hand side is French, and it's attending to different positions in English. It turns out this is only one type, and it's like the paper's title, attention is all you need. And encoder has some self-attention, which means if I am on the third word, I can attend to the entire sentence of the English. We're only talking about English here. Like, I am a student, am is attending to I, because if the subject changes, become he, I might become is or something. So they are correlated. So in here, it's essentially on the source, this is called self-attention, everything attending to itself. And in the target, this is the interesting part. In the target, you have some kind of more orderly attention, which is called vast self-attention, because like I mentioned, you can only look things that has already been, that is in your, what is that? That thing happened before.
Already been output. Already been output by you. You can only pay attention to things that you've already output.
Yes, you can only pay attention to things that's already produced in a way, in output. So there's like a subtle difference, which I think we'll be seeing that in the code. Okay, any questions about attention so far? Okay, by the way, these pictures, these 3 pictures are stolen from the one of the authors who gave a really good presentation on this. I suggest check it out. Yes.
So for the masked coder, is it looking at things that you predicted, or is it looking at the ground truth?
Ground truth.
Okay.
Ground truth in here. So this part and this part, they are both ground truth, which is because it's supervised learning. So those are ground truth. Okay. Yes.
That's about your training, but when you're running it, not when you're like evaluating.
You're inferencing.
Then it's going on itself, right? Yeah.
Very good point. Yes. You're going in the self, and you have to do. I'm going to show like greedy decoding that part. So but still, it's sort of like I produced a first word and second word, and then you feed that back into yeah, you're correct. You feed that back into the that word. That's doing what happens during the inference time. So self-attention, like just to make things easier, Felipe suggested that I just annotate all the dimensions, because dimension turns out to be a really good aid at understanding it. So this is pseudocode. This is not actual code, but this is essentially 2 types of attention: encoder-decoder attention and self-attention. What I want you to notice now, for now, is this is a 4D tensor, which you probably won't be able to see in the math formula, but it's a 4D tensor. I'm going to explain what these numbers in. We are already familiar with 512, which is our vector size everywhere. Whenever we have a vector, it's 512. And we have 64, and we have 8. So where do those come from? That's where we're going to get into that. But usually, when you train these things, you have an extra dimension, which is your batch size. I forgot their batch size, but that batch size really depends on how many GPUs you have, I think. How much memory, okay, yeah. So, but essentially, both self-attention and attention, and I'll call this Q split, because it's being split, which I'll explain. Just do remember, when we're working on this, it's 4D. And how do you do matrix multiplication in 4D? Turns out that it only works on the last 2 dimensions and keep the rest the same. I think if you But if you just by looking at the code, you won't be able to see. But and then you look really carefully, and then you realize it's 4D. So again, that's exactly the same picture. So here is our generic attention. So this applies to both self-attention and the multi-headed attention. And again, we have a 4D query key and value that as the input. And here we're doing something called DK. In here, I'm not hiding it, but D, remember, is essentially 512 at this point. And here, optionally, you can have a mask. The mask is what we talk about. You can apply any type of mask. For us, it's just masking everything that hasn't happened yet. And you essentially do a mask fill, and then you apply a softmax, which exactly corresponds to this architecture. And finally, you get an attention map, which is here, S means the length of the sequence. So attention map is the length of your sequence. So for any source of code, I think in theory, the source and target could be of different sequence length. But in the paper, from all the implementations I see, just for the sake of simplicity, they're the same. So I'm highlighting the same. So it's essentially, given a target position, which source position I care about. They could be different. So some language is longer than the other, or shorter. And eventually, this attention outputs is you apply this attention map back to the value. And I think can people help me out here? Like what? Okay, essentially you go back to the pretty much the original dimension. So the input and output dimension is this dimension is the same with this dimension. Okay, good. And here is the multi-headed attention. So remember we talked about like where do this H and where does this like additional H come from? So it turns out in the paper they do a split and merge strategy. So what that means is on a very high level, because I think we talked about this like in the other session. I like to think of, may not be accurate, but I like to think of at a high level as some kind of instead of having a one all-powerful person to do the things for you, you split him into multiple millions. And then each of them doing a little small thing, and eventually you merge them. Sort of like ensemble weak learning. That's the way I like to think about it. It may not be accurate. So this is why you do the splitting. So yes.
So I don't know. I have a different understanding perhaps, but
Yes.
is this because you want to learn more rather than just, let's say you want to learn X and you are dividing it, right? So that could be one thing.
Yes.
The other thing could be you want to learn X plus Y. So you want to learn more. That's why you are doing this, is it?
That's a very good point. Yeah, because they do eventually when they merge and they add to it another layer of probably nonlinearity. That's a very good point. Yes, essentially you learn more. Yeah, you can think of that. So that's why they do split, because the author said empirically splitting gives better results as opposed to like one attention head. This thing is, they call it attention head. Instead of one attention head, they use 8. So that is why, that is essentially here, why you see this. This is hyperparameter H. Oh, you have a question? Okay. And then the way you do splitting is essentially you, I think they want to keep all the dimensions same. So like the input and output dimensions same, so they split into 8, resulting, originally you have 3D. That's why now you have 4D. So you add an extra dimension, and you have 8 things of that dimension. And it turns out, like we explained, you can still do multiplication in 4D, and eventually merge it. So the way you split and merge, practically speaking, is you are doing reshaping. I'm looking at, where's the reshaping part? This is, I think this is the reshaping. Oh yeah, this is reshaping.
With BLEU, yes. With BLEU, you do reshape, yes.
With BLEU, so okay, for those not familiar with PyTorch, yes.
You said 8 things. What things?
8 attention heads.
8 separate sets of queries, and like, or 8 separate sets of the multiplication operation is what you're saying?
8 sets of value, key, and query at the same time. I think.
And that's only in the decoder, or that's in both? Because
it's everywhere. Self-attention, encoder-decoder attention.
so,
Yeah.
for example, in the self-attention thing, from what I saw in the code at least, it looks like they're just using x a bunch of times. So is that 8 sets of x being multiplied by
Okay.
itself?
That is after, because I saw one implementation where they use multi-headed attention or self-attention, and another where they don't.
Okay.
So
Is it
I
possible that all the x's then were not multi-headed?
Oh,
Because I don't
actually-
know why you would want 8 sets of the same multiplication.
you want 8 sets of the same amount. Sorry, can you speak up?
The idea was that the weights were initialized differently, but if it's the, I mean, okay, yes,
That's a good question.
Yeah, but that's also a good answer.
it's a good answer, yes. If you're just actually saying that there's actually 8 different sets of output, then 8 different sets of weights, so that 8 should be through the whole system then, one would expect.
Yeah, it should. Actually, I was wrong. I was wrong on my previous comment about sometimes they split self-attention. I checked later, and actually, I think they all split. All the implementations all split. I think.
It does, as long as the 8 is consistent, it doesn't matter. I just was like, I don't know why you would do 8 of the same, using the same sets of embeddings from the same thing. Like, it wouldn't make any sense to me. But
Okay.
if they're different, then that makes sense.
Okay. Yeah. Okay. So, for those not familiar with PyTorch, so view is essentially reshape. That's what a view is. So you split by doing reshaping from 3D to 4D, and at the same time you do a merging by converting that 4D back into 3D. That's essentially doing the splitting.
If you want to stick with your TensorFlow, I think if you still print that reshape, I think it will still work.
If you just change that to reshape.
Yeah, I think it will still. That's as an alias for people.
Yeah. Okay. They copy each other all the time. Right? Okay. And
Chang, I have a question.
Sorry, I think it's kind of similar to his, but so are the value, key, and query input the same for all the heads?
key and query input has. I don't think, but by the code, I don't think that's the case.
That's not the case?
For self-attention, I think it is.
Okay.
Or at least it seems to be, because there's a point where it says self-attention XXX.
Okay.
Oh, sorry, I was talking, thinking of differently. Yes, you're right. For self-attention.
That was the question, because I'm.
Is that the question?
Is the value, key, and query the same for all the attention heads?
Oh, okay, that's I totally misunderstood the question. Okay. Yes, self-attention XXX.
Okay.
Exactly, key, query value, exactly the same thing.
Okay.
However, for encoder-decoder,
It's different.
Query is from encoder, but key and value, they are the same thing.
Yes, and their M, whatever M is memory, the memory embedding.
M is memory. M is from the encoder. So you have self-attention XXX, and for the other attention you have XMM. So you might, this is probably unnecessarily abstract because like it essentially key and query, they're the same thing, right, everywhere. So yeah, sorry, I totally forgot that point. So in addition to that, there's that small detail, like they introduce a linear layer here, probably just to add capacity to the network before they feed that into the scaled up product attention. So this is, again, as a software engineer, I don't like the code because it's clever, but it's not clear. So like the way you do that is like you have a bunch of linears and you clone them 4 times. So it's like, where does the 4 come from? And then it turns out you have, you need a linear here, here, and here, and finally an output layer, you have another linear. So they're like, oh, to simplify, probably I just do it in 1 line. And then you can get lost sometimes. Like, and here you can see like the last thing from the linears which is this thing, that's how you apply it. But other versions are more clear. Okay, let's move on. So here comes the masking. Actually, I might have mixed this, maybe come from another implementation, but I think if you just plug that into the N30 transformer, it will still work. But I think this is more clear. That's probably why I put that into here. Actually, it's kind of straightforward. So basically, you are utilizing this NumPy function called triu, stands for upper triangle. And you supply a k value. So here's a small experiment of what it looks like. So you have a 3x3 array, and you supply k with 1. You get this upper triangle matrix where all these things are 0. And another detail which is interesting is that I think np.foo, what does np.foo do? np.foo supplies a matrix of this size you supply. The first parameter is of this size. And the second parameter is the value. You might be thinking like, why not 0? Why is it supplying negative infinity to the mask? So effective, if you execute this, instead of this, all these 2, 3, 6 numbers becomes negative infinity. Your diagonal is 0, and your other values are all 0. Could anybody guess why they use negative infinity?
Does it have to do with the activation function?
Has to do with that. It's close. So remember, after you do the masking, what do? You do a soft mask. So this is a clever trick to actually to say, I think if you do this, run this through softmax, it goes through softmax, negative infinity becomes 0. So because in mask, you're basically, you have variable number of things you want to care about. I think if you just apply it with a negative infinity, it turns out to be 0. You don't need to kind of renormalize your output, like give it like various size output, if that makes sense. So it's just like a small trick. Okay, and you do unsqueeze and unsqueeze. Unsqueeze essentially means reducing dimension. A lot of times, I think what's the equivalent in Tensorflow? I forgot. Oh, it's still unsqueeze, I think. Squeeze and unsqueeze. Oh, sorry. Unsqueeze is actually adding 1 dimension. Squeeze is actually reducing 1 dimension. So this actually added 2 dimensions? Okay. You add 2 more dimensions, why? Oh, because it's 4D? Is that the reason why? I think, okay, that's probably the reason. And there's the other part. So that was all the attentions. so I think we're pretty much done with attention for now. And then after it goes to this complicated self-attention, we're looking at the encoding part. It goes to this thing called position-wise feed-forward. The reason you want a feed-forward network, just as a lot of other architectures, is you want to add, I guess you want to add expressiveness to the network. So you introduce a certain new layers of non-linearity to add up to the capacity of the model. However, the interesting thing they're doing is it's position-wise. So this is no different from a regular feed-forward network, or maybe it's a 2-layer feed-forward network. However, it's position-wise, but the code is exactly the same. By position-wise, I mean every single position is applied to the same weight. So if I have 20 positions, it's the same weight, and they're kind of shared across positions. So, but how can you do this with the same code if you want to do position-wise? It just turns out if you just run it and it works. Any guess why? Okay, I think the reason is because it is doing some kind of broadcasting. That's my guess. And because you have, I lost track. So the last 2 things you input, like if your x is your sequence length plus your 512 vector length, and this is the usual output. I think I mislabeled here. This is the usual. However, if there's some kind of extra dimension here, as a result of multi-headed dimension, if there's 8 here, it becomes 4D. And you just feed that into that, and you do your usual nonlinear thing, and it turns out that it will, what it will do? It will replicate 8 times. Is that? Oh, sorry. It will replicate into every single position. Oh, sorry. So this 512 gets decomposed into 8 times 64, which becomes the new dimension for a little learner, and 8 things. And you feed that as long as all the previous things are kept the same, I think it will just do a position-wise straightforward neural network. I know this is not a very good explanation, but it just turns out it works.
So
if someone could count, yeah.
Just to summarize what you said, that from what I got, you're applying the same set of weights across the entire brick.
Position, each single position, each single weight.
Yeah, so what all position-wise means in this case is that you're duplicating the weights across. It's kind of like convolution almost, but not really.
Yes.
Right?
It's almost like one by one. Okay, yeah.
Almost like, almost.
I would say it's similar to bag-of-word in this case.
In what sense, bag-of-word?
In the sense that, when the attention, the output of the attention layer is injected the fully connected layer, it does not factor in the position of that word.
Correct, essentially.
So it's basically a bag word.
Yes, in that sense. I can't, if that's my understanding of what you're saying. Okay, yes.
I think by bag of words he means some sort of n-hat encoding. In that sense, by bag of words we probably mean some sort of n-hat encoding.
I don't
because that's what bag of words is.
Well, when I refer to bag of word, I simply mean it does not consider the position and context.
Yeah.
I see.
Yeah, in that case, yes, because each position is applied independently. That's the original word, separately and identically. Question, yes.
So what is 2048 again?
Oh, sorry, I haven't explained this. So you have two layers, and the intermediate layer is like input 512, and in the intermediate layer expands to 2048. If someone could explain why they do this, other than network capacity, that'd be great. And then the output becomes 512 again, just to keep things persistent.
So from what I understand, instead of having a linear layer with a matrix W, here you have a linear layer with a vector and it's just a dot product. Is that correct?
Which one is dot
like
product?
W1 and W2 are supposed to be vectors?
No, those are
but
W1 and W2 are matrices. They're the weights of the they're usually. Like
but all of the columns or rows are the same? Because you were saying that.
Yeah, W is the same. W1 and W is the same across all the positions. Okay. So you've got 20 positions. So this is essentially this is math, and this is ReLU for those who. Yeah. So ReLU, is there ReLU here?
No, I think that.
Oh yeah, there's ReLU. Okay. So I think that those are the most. The other interesting part is this thing called positional encoding.
So you asked it. So you were just asking from us. You
Yes.
just increasing the capacity.
Why increase why? Again, other than why having more capacity?
Are you asking why is it 20?
Yes. Why do you do this expand and contract?
It's something that they've done. I've seen with autoencoders. I forget why you try to expand.
Noise the data before doing that.
Sorry, what?
In autoencoders, they usually noise the data before doing that because
Before expanding the space, yeah.
Okay, I gotta check the time. How are we on time? Oh, 7. Okay, kind of late. So I gotta move. Let's.
So we don't have a results section probably.
Yeah.
So just call it over sometime.
Whenever you think.
Okay, after position encoding, we take a break. So positioning is this part we have been ignoring here. Here's the positioning encoding, and remember, I think it is being applied to every single layer. I think it's every single layer. Let me check quickly. Oh, it's not. It's actually being applied to the input, and this. So just being applied to the inputs. So the reason you're doing precision encoding on the higher level is because from the original RNN, you automatically, you input one thing at a time. So there is this implicit temporal and positional awareness, because I know what comes before and what comes after. But if you do everything in parallel and all the tensions being applied to everywhere, there's no way of knowing, does this come from the very beginning, come from the very end, or if it's just a bunch of attention waves being thrown at me like at once, I look at these two things, are they close to each other? All that part is missing. So that is why a position encoding is added, like this is literally element-wise add, into each of the input to make the network aware of, okay, where where those things are. It's basically like if you do programming, you have index from 0, you have an array, and you have index from 0 to 100. You literally input those kind of numbers, add those numbers into the computer. Yes.
That was exactly what I was thinking. So why can't it be managed using the indexing? Like, why do we have to put something as a positional encoding? Any idea, any intuition about that?
If you do so what is different? Okay, let me explain this. Then we can. So I didn't parse all the math in here.
Can I give you a short answer?
Yes.
Is it not because you want your network to be informed by implicitly as well?
Network to be informed by implicit.
By the progress through the layers.
What do you mean informed?
So if you put it as one of your components, which I understood from what you were saying, you're going to do multiplications across the layers, right?
Yes.
And then your network, like your keys and values are going to be informed by that position of putting as you want.
Yes.
Is that so? To me, that's.
But his answer is why not do this complicated thing? Why not just literally use numbers 0, 1, 2, 3, right? That's your question.
Oh, right. I see.
I know we can discuss this later.
I can answer. I actually can answer.
Yes.
I mean the graph.
Okay, sorry. Can I explain this first?
Go. do that.
Okay. But what is precision encoding exactly? They use this kind of weird, some of you probably know, sinusoidal. What is a cosine? The cosine-soidal thing. For like for each, like every odd position, they use sinusoidal. For each even, oh sorry, this is, I'm not saying that odd. I think it's for each odd dimension, because for each dimension there's a position value. So each odd dimension they use sinusoidal. For each even dimension is a cosine sinusoidal. So the end result is you have a combination of a lot of these values. I think this is really good for like parsing relative positions. Like say if I'm on position 20, my dimension 5 value is very low. My dimensions 4 is in the middle, and so on. And if I'm moving to 21, I compare that with with 20, they are very close to each other. I think that's one of the reasons. So like then you have this relative position, and in addition to that, hopefully by adding to all these numbers, each position has a unique combination of values. I think that's right. Yes.
So the basic intuition is correct, but I mean, if you think about it, all you're trying to do is you're trying to make it so that the notion of space, as you change the embedding structure to the network, that positions, like the overall structure of the embedding changes with the value. Does that make sense? You're actually trying to decompose a notion of number, if that makes any sense, or have a more distributed notion of number. So by having your number represented as basically a frequency, right, that has all of these sub-elements, then as the frequencies become more similar, the numbers become more similar. But as they become more different, they become a bit more different, right? And you also get relative notion. And the point is you're trying to have a distributed notion of number, basically. If you want an embedding for a position, you don't want your embedding to be one value because it will be discrete then, right? And then you'd have gradient problems, blah, blah, blah.
Oh, gradient problem. That could be the answer to your question.
Right? You don't want categorical data. That's why we swap immediately out of one hot vectors as soon as possible.
Categorical.
Right? You don't want categorical data.
Yeah. But okay. What he's suggesting is not categorical because he added those numbers. There's
True.
we can talk about this.
You would have a single.
Okay.
We'll talk later.
Okay, sorry. As a moderator, I have to self censor. I have to move on. Okay. What I want. So before I take a break, last thing, you see the requires grad equals to false. This is an interesting point because if you look at this entire thing, there's no parameters to be learned. It's a fixed table. You can pre-compute it. So the author actually, they tried two things. One is they add some learn the parameter into the mix. And the other is this. And they realized empirically there's no difference. So there's no point of introducing any additional parameter. This is expressive enough for whatever frequency, for whatever reason. This is good enough to, as a positional encoding, you don't need to learn anything, and this is pre-compute as a table. As a result, like was mentioned a few slides back, a PyTorch requires grad is set to false to suppress gradient computation because it would otherwise be a waste of time. Okay, let's take a break. Oh, thank you. What about in the middle? Okay. Hello, hello. Sorry? It's too close? Hello, hello. Hello, hello, hello. Testing, testing, testing. Oh, really? Hello, hello. Is that okay? What about, oh, they have to become like, okay, how about now? Okay. Yeah. Okay, for your case, I still have to, I was going to ask you, like, depends, would you rather do code review style or you want to present regular paper style? Oh, no, no. So that's why it's again, it's up to you. That session is code review, but it doesn't have to be code review.
Are we good? All right. All right, let's move on. Oh, any questions so far? So far. From Mark.
Sorry, well, I'm not sure if my intuition is correct. My feeling is that this weird positional encoding is somehow related to, well, the fact that convolution is in the harmonic space is equivalent to, sorry, convolution in the time space is equivalent to multiplication in harmonic space.
I don't know. So maybe that's a comment. We can get back to this point, but it's definitely interesting. So, but okay, let's move on. Layer norm. They chose to apply layer norm. If anyone know the literature about layer norm, please enlighten me why they picked layer norm specifically. But I think they said it's easier to compute than batch norm. I still don't get why, but I thought they would be the same. But I still haven't thought this through. But essentially, layer norm is just basically a straightforward implementation. You have two parameters very similar to batch norm. Instead of applying to batch, you apply layer-wise, and to normalize the values like in a single layer. So everything put together. Essentially in here, there's not much more to talk about. So essentially, I should have put the graphing here, but essentially it's everything stringed together. I think it's straightforward. Things goes in from attention, and then it goes through multi-headed attention, position-wise 3-4 network. In here, this is how everything goes from, first you have an encoder, and you have a decoder, and then add some embedding. I think we've looked at the encoder-decoder part before. So this is basically where you pipe everything together. Fairly straightforward. I don't think I have any other comments. And if you don't understand this, this is not really straightforward because you don't know what these parameters are. But you could also always refer back. That's why, again, this particular implementation is just too abstract for me. So when you train it, this is your usual training loop. And I guess this is one of the reasons why people like PyTorch is because everything's so explicit. You can get that for TensorFlow Eager as well. Here is the loss function. It's abstracted out. This criterion here, I saw cross entropy and I also saw KL divergence. So it could be one of these losses. What else? Oh yeah, just a little preliminary on how gradients computed and applied in PyTorch. Typically, you have a you just basically keep applying your value, like x equals to network, x equals this layer, and gradient keeps accumulating automatically. And at a certain point, you do a optimizer dot backward, which flush out all the gradient, applies your gradient, and after that you do a zero grad, which basically resets all your gradient computation. So everything is very manual and very, I would say like it's explicit in a way. And if you look at a new TensorFlow Eager, you have something very similar. They call it gradient tape. So that's essentially what they're. Oh, is it computing the gradient here? Oh yeah, here. This is where you first you move forward. You apply the criterion. You calculate the loss. Some gradients gets computed along each parameter, and you do a backward. This is where you actually apply the gradient and reset the gradient computation. Every single step. Again, this code is the same with the code here. Next slide, just to show you some results. Loss function is loss value is decreasing. That's all it's saying. By the way, this is run as a, this is for a toy example from the code base. And this part is, I think like they mention is important because without, I think this is called scheduled learning rate. Without a learning rate that's dynamically changing, they said they would not be able to train this. That is kind of interesting why. So the scheduled learning rate is essentially they have something called a warm-up period. And after warm-up period, and then there's like a gradual decrease in the learning rate. So these three lines correspond to three different configurations. The 512 and 512 correspond to the length of your vector across the board. Like we have been looking at 512, I think the all also around 200, so 256.
We claim that it's mandatory, that it's necessary to
in the annotated transformer, I think they mentioned that, but I don't remember seeing the original paper. It is?
Yeah.
It's not, or it is?
I think it is.
Oh, it is. Okay, I don't remember. But from the annotated transformer, I think they mentioned this. Like, this is very important. Without this, like, this will not work or something like that. You don't think so? Okay. So if anybody could explain why this learning rate scheme is important, I guess from a higher level, maybe at the beginning you want things to run as fast as possible. Maybe the more important thing is like gradually gonna dial down. Maybe that's the more important part, but that's what happens empirically. And in the actual PyTorch implementation, the way you do that is they have a custom class called NoAtom optimizer. NoAtom, I don't know what it stands for. But what it does is takes in the canonical atom optimizer, and then they do some very manual tweaking in here. And oh, sorry, there's a part that's got blocked. But this function essentially computes the rate given time. So there's a part that got included. That's why it didn't make sense. Okay. But that's basically the idea, and this is the math formula concretely. This is slightly more interesting multi-GPU training. So what we saw here is how you do it in a single GPU. And the annotated transformer also gives multi-GPU training. I haven't run this personally because I have only one GPU. But this is supposedly how it works, and they have code for that. On a very high level, it is a combination of splitting your things inside your batch, replicating the weights across GPUs, do the computation, and then kind of merge back the result. It's called a gather. So you have replicate, scatter, parallel apply, and gather. And they do it different, like for forward pass and backward pass, they do it differently. This is kind of picture I got from the internet. The post is no longer there, so I only have a low res version of it. I hope it's correct. So essentially, you do a split and you do a replicate, and this is part where you do parallel apply, and then eventually you gather the results. Because I haven't run this because I'm not very knowledgeable on the details.
So what are you parallelizing?
This is essentially issuing command, I think, to all the GPUs, say, just do the computation. You're parallelizing
The
essentially,
batches?
inside a single batch. Say your batch is 32. And then if you have two GPUs, you split them into what? Into 16 and 16. Ideally, you will have 32 GPUs. But but I think there's some kind of like practical limit as to how many GPUs they have to do.
So from scatter, it seems that they're splitting over batches. So one batch to one GPU, is this, or a few batches to each GPU?
I think it's a single batch you split.
Split batches.
Because like
Because
you split to certain
the batch, the
Each
concept of the batch is like you want to do it in parallel, right? And then move on to the next batch. So the way you do it, a parallel, because you have two GPUs, if you just dump everything into one GPU, it's a waste. And then so you split your batch.
So you're splitting the batch itself, single batch.
I think, yeah. I think. Oh, because I actually have code. Let's look at code.
Okay, yeah, let's look.
So replicate is essentially, I think this replicates the memory allocation of maybe something like across many GPUs, so that every GPU is ready. And then this is where you look scatter. Where is the out? Oh, I don't have the definition of out. But I would say this is like usually one pass, like we call it one forward. So I would say it's batch. It's a single batch.
Do you think that's maybe why it's doing the layer norm instead of batch norm? So it can parallelize it more?
Maybe. Maybe. I don't know. That's a good point. I haven't run this. If anyone has like 32 GPU or something from Bitcoin mining, or just try this. And sorry, I didn't really totally completely comprehend this code. So, and eventually I only highlight the part I think is important. So eventually, like when you try to get a result, this is here you do gather, and I assume this out graph that's an array of a few maybe abstractions, so that's why you have to explicitly call gather, so that this becomes concretely like a variable that you can get value from. And so that leaves question. So there's this.
So like I make a comment. You tell me if you agree, but I think Tensor is traditionally my TensorFlow may be overriding my PyTorch right now, but you have tensors on GPU type tensors, and you have tensors on CPU. When you gather, I think what's going on, well, CPU is technically on your memory, right? Mm-hmm. When you gather, I think that's what the transfer that's happening. So you're gathering from your GPU tensors into your CPU, which is your memory.
It makes total sense. But why do you not need to do gather in the single GPU? Because you still need that operation, right?
Like, don't you want to merge them all at some point into your batch and an output perhaps?
Oh, you're saying, okay, so when you gather, you're actually copying from many GPUs to one.
Yes, and that's also like saying that using multiple GPUs is amazing, but that gather and scatter is a bottleneck. I mean, it's not like you actually compute things 8 times faster.
Could be.
Because moving data is costly.
It might be better on a TPU, so.
Fair enough.
Sorry. I thought in latest TensorFlow, the ring reduce paradigm has been fully.
Sorry, I'm cut.
Okay.
Okay. Well, we can come back later.
Okay. No.
It's not relative.
So the NLP transformer uses greedy decoding, but in the paper they use beam search. How many of you have got a rough idea of what beam search is?
We have also a video on it.
We have a video on beam search, but okay, I tried to explain this before, and then you helped me. I'm gonna try again. So very roughly, when you are actually doing the inferencing, like Lindsay, she was here just now, made a comment. You want to produce your first word, and then you take your first word and take that as the input of the decoder, so that your decoder is aware of what decision you have made previously, and you move on to the second word. So there's that being fed up. So it is, training is parallel, entirely can be parallelizable, but in inference time, you still got to do this a lot of time one by one, just because you have no idea what you produced from previous one. You might have a guess, but with various different schemes, you might choose to pick something differently. So that is why there's this inherent iteration. So very roughly, what beam search does, as opposed to greedy search is very simple. I produce the thing, I take it as my next output. So practically speaking, what ends up happening is that it cannot look very far. So it produces weird sentences like, I am a tree, a tree house cleaning. Because something like that, like I am a tree house cleaning. If you look at those adjacent words, tree house, house cleaning, I am a tree, they all make sense. But across the time span, like, because there's a very lack of context. So that's why you need beam search. Beam search is essentially helps you look a little bit more ahead, more distant into the future, into the history. So you got more context. the way you achieve that is you implicitly basically compute joint probabilities across like in history, and you consider jointly what has happened in the past. So the way you do not blow up your memory, because combinatorically this grows exponentially as your step move on, you always truncate the top probabilities as you move on. That's like beam search in a nutshell. Does that make sense roughly? Okay, cool. So, but they said it's too complicated. They don't want to do it. So we have this greedy encoding, and the example they use is like very simple. They're actually trying to not. This is also not a translation task. This is repeating number. So this is basically input is 1, 2, 3, 4, 5, and output they say, okay, yay, 1, 2, 3, 4, 5, 6, 7, 8.
So the actual work does actually implement beams.
The actual word at implement and with a beam size of 4. Beam size of 4. I think that means you keep 4 things at a time.
Correct.
Yeah, that's
which is
beam
great.
size. Okay, I think we're up near the end. So the original implementation, since then, I look at their source code. It's nearly 3,000 lines long, and not even including the attention part. And they added, since then, a lot more optimization based on later paper. So I was just like, okay, there's no way. So I didn't look at it, but from what I've read, but I know that's like very production ready thing. It's like high grade, like production ready code. So they took a lot more things into consideration. So feel free to check it out. From what I gleaned from the code, they support 3 modes: TPU, GPU, CPU. They actually have if TPU do this, otherwise if GPU do this, otherwise do that. So a lot of those things, and then they cache the computation of attention map. I haven't figured out, like maybe there's some parts where caching makes sense, but I haven't quite figured out which part. But they do something like caching, because I actually saw the caching, and I think it's based on TF estimator, which is a scheme that they use for if you use TF estimator, and then you that's pretty much the only way you can use TPU, I think. You have to fit into their TF estimator like kind of paradigm. So it's like higher level API. All right, and finally, thanks for some of our friends, Ren Yu and another friend, for preparing, help me prepare. And thanks to Rosebud, is he here?
He was there.
He was here. And Dave for giving some suggestions, and definitely thank Ehsan and Felipe for giving a lot of suggestions. And here is the reference. I think every single one of them is good. We're basing on added transformer, and there's a lot of pictures in illustrated transformer. The one that is really, I think really explains things really well in terms of code is the second to last one. And finally, the last one happened this morning. So I added it here. But that's a much more concise version of what we saw. And it kind of distilled idea of, it's very, I look at the code, I'm like, wow, is this short? And then they are managed to implement like very basic idea of transformer. Oh, this one, I didn't have time, so I didn't prepare. That's all. Thank you. Okay, so if anyone